In this video, I'll be talking about the potential due to a point charge. Let's say you have a point charge here, Q, and we are interested in finding out the potential difference between the 2 points A and B. Or we are also interested in calculating what is the potential at point A, what is the potential at point B, or what is the potential at any arbitrary location due to this charge. RA and RB are the location of point A and point B with respect to this charge. So in order to calculate the potential, if you recall the formula, the equation, this is the formula for calculating the potential difference. AB means the potential difference between point B and point A. That's how it is defined here. If you go from point A to point B, that this is the potential difference. Alright, here we're just moving from point A and point B and we're calculating the potential difference. Okay, and E is the electric field at any location. Okay, and you see that E is not constant. Just remember, E is not constant. Here E is not a constant, so you cannot take it out. And E dot R, and in this case, E dot R is simply equal to E times dr, and the cosine theta, in this case the cosine theta is 0. Cosine theta is equal to 0, so it will be 1. So this is simply equal to E times dr. And why it is the angle is 0? Because if you look at any point, this is the direction of the electric field due to a positive charge. For a positive charge, the electric field is always radially outward, and we're moving the charged particle in the same direction. So electric field and the displacement are in the same direction. So the angle is 0. And again, electric field is not constant. So how do you know the electric field due to a point charge? So the electric field due to a point charge is given by KQ over R square. And that's what we have written here, KQR square here. And here the R dot, this R hat, the way we read it is R hat gives you the direction. In this case, the direction is this way. Okay, K is constant. The value of K is 9 times 10 to the 9 Newton meter square per coulomb square is a constant. And dr vector can be written as R vector times dr vector. Again, R hat is the unit vector, For those who have taken the calculus class, you see this anything hat with the hat, that means it's a unit vector. That means its magnitude is 1. So R, now we just taken KQ as a constant and we're just taking outside of this integration. And R dot R, this is simply equal to 1. So now this equation becomes this equation, dr over R square. If you integrate 1 over R square, what is the integration of 1 over R square? It is simply equal to 1 over R. If you need the formula for x to the n, integration is x to the n plus 1 divided by n plus 1. Use this integration. If you use this formula, then you'll come back to this equation here. Now the limit is from A to B. So after plugging the limit, this is what you get. What does this mean here? This means VB minus VA. Okay, so and now you see RB is greater than RA. So that means this potential is negative. Since RB is greater than RA, this term will be smaller than this term. That means it will be negative. And it makes sense because the potential at this point has to be smaller than the potential at this point. As you go away and away from this charge, if you go away and away from this charge, the potential has to keep decreasing. So now, then what is the zero potential then? Then the zero potential is defined when we go very, very far from the charge, a lot, like infinitely distance from the point charge. That is called the zero potential. So in this case, now we're going to define zero potential if Ra tends to infinity. If this point or Ra or Rb, if this tends to infinity, then what we get here from this equation is simply kq over r. Here we have assuming this tends to infinity. Then if 1 tends to infinity, then what you get is this term here, kq over r. Okay, so this gives you the potential at any distance r, kq over r. That means if you need to find out what is the potential at a distance r, at any distance r, then the potential can be simply given by kq over r. This is the potential due to a point charge. And remember, the potential is a scalar quantity. It does not have any direction. It is just the magnitude. Okay? And while the electric field is a vector quantity, the potential is a scalar quantity. Just keep this in mind. And it is simply kq over r. While the electric field varies as kq over r square, the potential varies as 1 over r. And now I'm just going back a little more here. Let's start from this equation again. This equation, in this equation, delta VAB, that means VB minus VA, and which is equal to KQ over 1 over RB minus 1 over RA. If you look at this equation here, that means VB has to be equal to this term here, and VA has to be equal to this term, KQ over 1 over RA. So this is the potential at point B, and this is the potential at point A. So what does this tell you? If you need to generalize these things, how do you generalize? That means the way you generalize is the potential at any point is given by KQ over R. And if R tends to infinity, then the potential tends to 0 as R tends to infinity. That means the zero potential is at infinite distance from the source. That is our reference point. When you go a lot far from the point source, then you won't be affected at all by the charge, or any charge won't be affected if it is far from the source. So this is it for the potential due to a point charge.